Hello, today we will continue discussing the concept of oxidation degree. In particular, we will focus on how to calculate this degree. To enhance our understanding, we will practice through exercises aimed at providing clear guidance on working with complex examples of redox reactions. However, before we proceed, let us quickly recap that the oxidation degree can be zero. For instance, a straightforward example could be the element oxygen itself. It's important to note that 0 is a valid value for oxidation degree. A metal, sodium, and that charge would be 0. The oxidation degree is written at the top on the right-hand side, in which case it is written 0 if it is a simple substance, not related to anything. It can have a positive value such as sodium in its compounds. +1. Or let's take sulfur as an example. In its compounds, sulfur can have a valence of +6 when combined with certain elements, but in nonmetals like sulfur itself, the valence would be 2. And for chlorine, for example, it's -1. And in the previous lesson, we explained that a negative oxidation degree cannot be less than -4, and a positive oxidation degree cannot be more than +8. So those are the limits of oxidation state applicability. Well, how do we calculate it? We must proceed from the principle that all particles in the molecule have 0 charge. So let's give an example. If we take a simple substance, aluminum, its charge, of course, will be 0. If we take, let's say, its compound aluminum 2O3, it is aluminium oxide, then how to calculate the degree of oxidation in this particular case? Well, you have to know the rule of the element to start with the calculation. It is the most electronegative, and it is usually at the very end, that is, at the edge of the form is the last. This is the order of writing formulas in chemistry. Let's start by focusing on oxygen. To determine its charge, we must determine which group it belongs to. Oxygen belongs to the 6th A group or the 16th group in the modern periodic table. It is 2 electrons away from having 18 electrons, which is the total for that group. Therefore, its charge is -2. Now let's move on to calculating the charge of aluminium. We'll take its charge as x, but since it has an index of 2, we need to multiply 2 by x because the index is multiplied by the charge. Next, oxygen has a charge of -2, but we have 3 such particles. Then the total charge must always be 0. That's a rule we can't forget. If this is a simple substance, a non-ion. Then from here we solve the equation with one unknown. We get therefore the charge of aluminium +3. But look, in this example, a rule you already know works, called the rule of the cross. When the charge of oxygen, the numerical charge coincides with the index behind aluminium, and the numerical charge obtained oxidation degree of aluminium coincides with the index of oxygen. But the rule of the cross does not have application in all cases, so please be careful. The following example, CO3. Which element should we start with? We'll start with oxygen. Its charge is -2. Then what would be the charge of sulfur? Then it would be x -2 times 3 equals 0. So x would be +6. Can these calculations be done in your head? Of course you can. So try to do such calculations on your own without the help of a special note. But if, of course, you are in doubt, it is appropriate to make such a record. So, the following example. Carbon monoxide is 2, so oxygen has -2, and I draw your attention to when the indices inside the formula are equal to 1, then the charges will always be numerically the same. Only the first element will have a plus charge, and the second element will have a minus charge. But in the sum, we stick to the rule all the time. The sum must equal 0. Next example. P-chlorine 5. Phosphorus chloride 5. Okay, chlorine has a group of 7. It's 1 electron short of completion. And then through the rule of the cross, phosphorus will have +5. This is where the rule of the cross works. Next example, tungsten O3. The fact that in the formulas there may be elements that are not very familiar to you should not frighten you in any way, because there are always elements that you can fall back on. This is usually oxygen. Oxygen has a -2, and then the total charge you get for tungsten is +6. Next example. Magnesium, 3H2. Magnesium nitride. Let's start with nitrogen. Nitrogen is in group 5, group 5A, or group 15. It falls short of completion to 8,3. And as we can see, the wonderful rule of the cross is at work here. So magnesium will have +2. Another example, let's say sodium. 3P, sodium phosphide. Then phosphorus, it's just like nitrogen, it's in group 5 or group 15, -3. And again, through the rule of the cross, it will be +1. Well, here I would like to draw your attention to the fact that an element with a negative charge, it is usually located at the end. But there is an exception to this rule when an element with a negative charge can be in front. Such a molecule known to you is ammonia, which is always written exactly in this notation, NH3, although the true spelling of this formula is, it would seem that that's what it should be. But historically, the formula for ammonia is written contrary to the formal rule that there's a minus at the end. Then hydrogen has +1 here, and through the rule of the cross, nitrogen has -3. In the same series, for example, the formula NH4. And here too, we start with hydrogen. Here it will be +1, and so nitrogen will have -2. From the same formula are exceptions when the elements are not in the same sequence, such as phosphine, pH 3. Here hydrogen is +1 and phosphorus -3. Now it's crucial to be aware of these exceptions as they are quite common. Therefore, always exercise caution and attentiveness to determine if your example falls into this particular category. Now, let's delve deeper into learning and calculating the acidity level in more intricate examples. Let me explain this within the context of nitric acid's formula. We approach the math in exactly the same manner as before, where oxygen carries a charge of -2. Then we take hydrogen as the second element to calculate, and it has +1 in the first place, of course. And oxygen is the most electronegative, so it's in the last place, and then we calculate it through the equation. +1, nitrogen we don't know yet, let's denote it by x minus 2 times 3, and the total is 0 again, just like we're doing here. Then we'll have an equation with one unknown, and then we'll have on the right-hand side, we'll have +6 at carryover -1, and so nitrogen will have +5. Writing down an equation like this each time is not necessary at all. If you are able to perform it mentally, it would greatly impress and benefit you. You have the capability to independently perform such calculations. Next is sodium 2SO4 sodium sulfate. Let's begin with oxygen 2, which is now the first element. Now consider sodium in the first group, so it becomes sodium +1. Sodium's charge +1 is then multiplied by 2. Next, we have sulfur X with an initial unknown charge. The charge of oxygen 2 must be multiplied by 4. The sum of these charges equals 0, which allows us to determine that X for sulfur must be +6. So the next example, calcium, CO3, and that's chalk or limestone or marble. That's the formula for one substance that goes into these unusual mixtures that we use with you. So oxygen has a -2, calcium is in the second group, so it has a +2, and if we do as a verbal calculation, we conclude that carbon has a charge of +4. Next, let's explain how it will work in formulas with parentheses. For example, let it be the formula magnesium. Twice. How do we work with parentheses? Exactly the same way we would do the math. So oxygen minus 2 plus 2, because magnesium is in group 2, and then the math would go like this. Plus 2, nitrogen we don't know yet, x. But since there is a 2 behind the bracket, 2 multiplied by x minus, and then I strongly advise you, so you don't get confused, the number 2, the index times the index behind the bracket and the charge that oxygen has, the total is 0. So from there, x is going to be equal to plus 3. Again, you're doing these calculations. Of course, I'd like you to learn how to do them quickly. So another example, aluminum 2, CO4 3 times. So if we do the math here, so oxygen minus 2, aluminum would be in group 3, so plus 3, and then we do the math, plus 3 times 2, plus 3 times x, minus 4 times 3 and 2 times 2, and the total is 0, so we always equalize by 0. And then from there, x equals plus 6. Therefore, this is the calculation for sulfur. Today we are here with you to discuss the determination of oxidation levels and how to perform the necessary calculations. We have just provided you with an example on how to create an equation with one unknown variable to simplify the process. This methodology can be utilized for both straightforward and intricate calculations, which we have recently covered. The purpose of this lesson is to demonstrate how this knowledge can be applied to specific examples involving redox reactions. This is why we have reiterated this point. That concludes today's session. Goodbye.